I am presenting the project which is called PANDA. PANDA stands for Powerful Advanced N-Level Digital Architecture for Electrified Vehicle and Components. The consortium is composed of University of Lille in France, Siemens Software in Romania, VUB University in Brussels, Valeo Company in France, University of Cluj-Napoca in Romania, Typhoon HIL in Serbia, TÜV in Germany, University of Bourgogne-Franche-Comté in France, Uni Research in Netherlands, Renault Group Romania in Romania, and Blue Waste in Belgium. So my presentation is composed of 4 sections. First, I will give you an overview of the PANDA principle. Second, I will present you some simulation results on battery electric vehicles, fuel cell vehicles, and plug-in hybrid vehicles. In the section 3, we will discuss about hardware testing of a battery. And finally, I will give some perspective of the PANDA project. So first, what is PANDA? So as discussed previously, we are working on the W model for the development of electric vehicles. And in PANDA, we propose a new open access model organization to organize the model in a cloud. And this cloud can be used in the 2 axes, virtual testing and real testing. The main idea is to reduce the development time by 20%. In order to develop this method, we use first the EMR formalism of University of Lille. EMR is energetic macroscopic representation, which is a method to organize the models of different subsystems. We will implement this method in the SimCenter AmSim software of Siemens, which is a very well-known software in automotive sector. And we will simulate and test 3 study cases, which are 1 electrical vehicle from Renault, is the Zoe, a fuel cell vehicle from another European project, which is called MobiPost, is from Université de Bourgogne-Franche-Comté, and also a plug-in hybrid vehicle, which is a demo car from Valeo Company. So globally, the framework is the following. First, we have the classical step of modeling of the different subsystems. Second, we have to organize all the modeling equations to be connected together. And we will do that using the EMR formalism. In orange, you have the system, and in blue, the control. And you can see that the control can be deduced systematically. It's also a way to organize the control. And in the third step, using the new EMR library developed by Siemens in SimCenter, we can systematically transpose this organization of models in the simulation software. What is important is that for any such systems, we can have different levels of models. For example, for a battery, we can have a very simplistic model for some task of the simulation, pre-design and so on. We can have a medium accuracy model, taking into account some resistive effect, thermal effect, and so on, and maybe a more complex model, taking into account electrochemistry phenomena and so on. And we can plug and play the model to connect the model to the other part of the simulated system. And to do that in an easy way, in a seamless way, we have to respect all the time input and output for this simple exchange. It is the case for the battery and other components, of course. It is called multi-level modeling simulation. So the different partners of PANDA developed the model of component. For battery, VUB, Blueway, and TÜV develop model of battery. For electrical drive, University of Cluj-Napoca and Renault developed a model of electrical drive, and Valeo too. For fuel cell, it is UBFC. For mechanical transmission, it is Siemens. And for control, it is University of Lille and so on. And all that model are organized using EMR for an easy interconnection. And moreover, it is capitalized in the cloud, which has been managed by Siemens. And now, using this cloud, we can simulate the 3 case studies, which are a battery electric vehicle from Renault, a fuel cell vehicle from the European project MobiPost, and a plug-in hybrid electric vehicle from Valeo. We can do the simulation in 2 different ways. The first way is called standalone simulation. That means that you upload the models from the cloud to your own computer and you do the simulation in your own computer. The second possibility is called cloud computing simulation. You connect it to the cloud and you do the simulation in the cloud without the need of an important, powerful computer to do that. Another key point of the methodology is that some model will be a black box model in order to ensure the IP of the user. For example, a battery manufacturer can put a model without knowing what is in the model to preserve the confidentiality of his product. Okay, let's move on more concrete work, the simulation of some of electric vehicles. So the first studied vehicle is the Renault Zoe from a Renault company. Globally, it's composed of a battery subsystem, an electrical drive subsystem, a mechanical subsystem interacting with the road. You can see here a very simple EMR of a low accuracy model. In green, you have the energy sources like a battery. In orange, you have the energy conversion systems like electrical drive, gearbox, and so on. And in blue, you have the control scheme. So from that EMR, we can build very easily the model of the battery electric vehicle in the simulation software, thanks to the library developed by Siemens. And we can select a low accuracy model or a medium accuracy model, as you can see. Both models are strictly the model for the same vehicle. Of course, we have to validate the model. What we done in that vehicle, for that vehicle, is Renault do some driving cycle in the testing track of RTR in Romania and record a lot of data. The velocity is recorded and is an input for the simulation. And we do some comparison in order to know what is the accuracy of the model. And for the different driving cycle, in terms of energy consumption, we have an error lower than 2%. At the system level, it's very good, in fact. Of course, we do the same for the fuel cell vehicle. The fuel cell vehicle is MobiPost, which is a postal vehicle for the French postal service. It has been developed by Université de Bourgogne-Franche-Comté during another European project. The vehicle is composed of a fuel cell, a battery, and 2 in-wheel motors. You can see in the slide the EMR of this vehicle and its associated control in the blue part. And of course, we can use the cloud of model in order to develop the simulation of this vehicle. And we have validated the simulation model from the driving cycle and the tests performed during the other European project. You can see that the energy consumption has an accuracy with an error lower than 4.5%. Of course, the model of a fuel cell is more complex than other part. And finally, we do the same for a plug-in hybrid electric vehicle, which is a demo car of Valeo. In fact, it is a retrofit of a classical diesel car. This car is a pure thermal car, and Valeo adds new subsystem, electrical subsystem, which are composed of a low voltage battery, 2 inverter, and 2 electrical machines. The objective of the study is to test the new subsystem using hardware in the loop techniques, to develop an efficient energy management strategy to reduce the fuel consumption, and to compare what is simulated and what is testing in hardware in the loop process compared to the demo car. Once again, we use a cloud of simulation in order to build the simulation model. At the moment, we have only validated this model in a pure thermal mode. That means only using the internal combustion engine to move the car. And in terms of energy consumption, we have an error on the fuel consumption lower than 2.5%. At the moment, we are doing some tests in order to validate more modes like hybrid modes, pure electric modes, and so on. Okay. All that simulation was in the virtual testing axis using pure simulation. Now we move to real testing, and I will present only the testing of a battery as a first step. What is the principle of hardware in the loop testing? We will upload the model of the studied vehicle from the cloud and to send it to a dedicated real-time simulator which has been built by Typhoon company. In this real-time simulation, we will do the simulation in real time of the complete vehicles, and this simulation will send information signals to a power amplifier which will deliver power to the tested battery from Blueway. And the objective is that the battery believes it is really connected to the real vehicle. So we can test the battery as it is in a battery, in a vehicle, sorry. So we do some tests. I will just present some. We try to replace the actual battery of the Zoe by a new one, the battery from Blueway, which is a high energy, high power density battery. And to have the same performance, we need to put 7 modules in series. And we have to check the compatibility in terms of performance and safety. Of course, the first step is to do simulation, but then we have to test the new battery. So we implement the simulation model of the vehicle in the real-time simulation of Typhoon, and we have interconnected one module of the battery through the power amplifier to the real-time simulation. You can see we do some tests with some reference driving cycle. It is in that case WLTC, and we have measured the behavior of the battery, including the current, the voltage, the state of charge, and also the temperature. And for that driving cycle, we can see that we have the right performance, but we keep in the safety margin without too big currents and so on, to high temperature and so on. I don't indicate that previously, but most of the results I presented are presented in the VPPC and specifically in the common special station. Okay, what are now the perspectives? Sorry, we are working on the test of the plug-in hybrid electric vehicles. Remember that the idea is to insert new electrical subsystem in this vehicle. That means that we have to simulate in real time all the other parts, including the IC engine, the mechanical transmission, and so on. We have succeeded in doing the test of the battery, simulating other parts, including electrical drives. Valeo has also do some test of one electrical drive. Electric drive means inverter and electric machine. And we are working to test all the electrical subsystem connected together. That means the battery plus the power electronics plus the electrical machine. So we try to develop an open method that can be used by other partners, and we start to develop what is called an evaluation group. So if some partners, external partners, would like to test our methodology for simulating other vehicles, other subsystems, and so on, they can do that. So we have some agreement to define together. The first company will be Sherpa company that will test the method for an EV charging station. We are finalizing the agreement, but it will be the first member of the evaluation group. So if some of you have some interest to test the method, it is open and we can discuss. So what is the final step is to estimate now what is the gain in terms of time to market using that methodology, which is important to convince people to use a new method. But I would like also to highlight that in this project, we have what is called a carbon care action. It's an action where we compute all the CO2 emission due to the project, including travels, video conference, testing equipment, simulation, and so on, in order to know what is the environmental impact of the PANDA project. And we will propose a mitigation action to reduce the CO2 emission of the project. So if you would like to have more information on the PANDA project, you can visit our website. Thanks for your attention. Okay.
Thank you, Alain. Thank you for your presentation. We have some questions for you in the Q&A box. So the first one is from Abdelali Samlali. So I don't know where you're from actually. But here is a question. What is the difference between simulation using software from Siemens and those using standard software like Matlab?
Okay. So in fact, in our project, we use both, but Matlab is more a functional software, whereas dedicated functional operator like first order transfer function and so on, and it's more dedicated to develop the control. AMSIM is more a structural software with a library of components. But in AMSIM, Siemens developed an EMR library, which is a functional description, in order to connect more models together. But the philosophy with the EMR library is to have a common framework. And we have connected some model from Matlab to AMSIM and so on. So it's another software which is very well known in automotive sector.
Okay, thank you. Likaibo have also a questions. So I open your microphone, Kaibo, if you want to ask your question, please.
Okay, can you hear me?
Yes, we can, yes.
Yes.
Okay, I would like to ask for the validation of the model. I saw that the 3 studied vehicles are only validated by 1 cycle. I was wondering if it is enough to compare only with 1 cycle.
In fact, they have been not validated by a unique cycle. If I take the example of the Zoe from Renault, they have they have tested for urban driving cycle, extra-urban driving cycle, highway driving cycle, and we have compared all the driving cycle provided by Renault. And some of the driving cycle leads to an error lower than 1%, and some of the driving cycle leads to an error about 2.5%. So globally, we have an interesting range of validation.
Okay.
And there is also another question from Kelly. I don't know if we have time to read it, if you have time to answer it, or if you prefer to answer it in the Q&A box.
No, maybe we can.
We can? Okay, so here is a question. Can we test wide bandgap power converters in your developed system to study powertrain efficiency? This is the first part of the question.
Yes, we use very classical power electronics today in the project because it is focused on existing vehicles. But it is sure that in terms of power electronics, we have to use a more efficient device like GAN or SiC. And one of the interests of the method is that maybe we can replace a classical inverter by a new inverter based on SiC on GAN, for example, to test what are the performance at the system level. So it could be of interest to have a partner that develop a new power converter in that aim. And the flexibility of the method will enable to do that.
Okay, then there is some other questions also from Kelly. So I ask them to you, what kind of model is needed, black box model or detailed device model, including device switching, etc.? And also, as wide bandgap devices switch very fast, would it cause any challenge on simulation time, complexity, accuracy, etc.?
So for the first question, black box model is depending on the IP of the user. That means that maybe in the black box model, you have a very accurate model, including the different effects, thermal effects, and so on. But people will not know the accuracy of the model. the idea is to keep the property. But in black box model, maybe you can have a very simple model too. It depends of what you propose and what is your need. In the project, we have the Valeo company that will keep the property of its electrical drive. They develop two levels of model in terms of black box. So we can adapt. The second question was about.
Yes, and the last part was, as wideband gap devices switch very fast, would it cause any challenge on simulation time, complexity, accuracy, etc.?
Yes, it's depend of the model you have. As presented by Reinhardt, we can have a complex model and simplify the model for having a system model, but maybe Reinhardt can complete. It shows that for real time it will be complex. Reinhardt?
Yeah, Alain, hi. Could you please repeat the part of the question that's still open after your comment?
What is the difficulty and the challenge to simulate SiC converter because there is a very high frequency?
Well, on the inverter side, we were mainly dealing with the conventional inverter technologies. Yeah, not going into deep dive on SiC side.
Okay, so it's an open question. Okay.
And then there is the last questions from Ronan Germain, University of Lille. So the question is, as the goal of PANDA is to reduce by 20% the development time for new EVs or new subsystem in EVs, and the question so is, in those 20%, what is the part related to the cloud aspect?
It's a difficult question. In fact, we are working on that point because one interest is to share the model by different group of development in order to avoid to redevelop in the different group the same model. But it's very difficult to quantify the time. But we are trying with Renault and Valeo to have an idea of this gain.